Ladies and gentlemen, my name is Zhenxu Zhao from Nanjing Tech University in China. It's my, it's my great honor to be here with you, participating in this grand international conference in the beautiful city of Spear. The subject of my research, of my presentation is effect of temperature gaseous carburizing on the fighting fatigue behavior of 316L stainless steel. And I will express my gratitude to my mentors, Professor Gong and Associate Professor Peng. This is the outline of my research. We are including 5 sections. We will start with the okay. Alright, please.
Okay.
We will start with the background procedure to experimental procedure, then fighting fatigue fracture morphology and analysis of fighting fatigue mechanisms, and we will finish with the conclusion. Now let's go to the first part. Fighting is everywhere in our daily life and industry production, such as in gas turbine, power cables, the train, and in the airplane. Although the displacements are very tiny in fighting, the combination of contact pressure and repeated microsliding promotes several surface wear, quick initiation, and even early failure. As shown here, fighting can lead to diameter road fracture, cable damage, wear axial seizure, and the fuselage skin cracking. So, the fighting damage is often described as the cancer of industry. Fighting fatigue, as a typical form of fighting damage, is characterized by very small relative displacements, high concealment, and yet extremely severe consequence once quick initiation. Fighting can shorten the fatigue life by more than 70% on the same stress level and reduce the fatigue limit by over 30%. 360L stainless steel is widely used because of very many advantages, such as excellent corrosion resistance, high toughness, and so on. But its no surface hardness and no fatigue limit make it poor fighting fatigue performance. So, optimal surface hardening techniques are essential for enhancing the fighting fatigue of 360L stainless steel. The surface hardening techniques are usually divided into surface mechanical treatment and surface thermochemical treatment. However, surface mechanical treatments are difficult to apply to the complex structure. The high temperature thermochemical treatment can form the carbide, which will decrease the corrosion resistance of stainless steel. So among these, low temperature gaseous carburizing can improve corrosion resistance, increase surface hardness, and enhance the fatigue limit of 360L. So, the fighting fatigue performance of 360L stainless steel after low temperature gaseous carburizing requires further investigation. This is the experimental procedure of my research. We carried out fighting fatigue test using a branch type fighting fatigue device. The normal contact stress was kept at 16 MPa. The loading frequency was 12 Hz, and the stress ratio was 0.1. Notably, the carburized sample were tested under the same conditions as the untreated ones. The metographic image shows that in carburized sample, a uniform participant-free 30 micrometers hardened case forms on the surface. The hardness and the carbon content shows a gradient distribution peaking at the 12 gigapar and 3.2 weight% respectively. The substantial compressive residual stress is introduced in the carburized sample, with 2.2 gPa on the surface. We performed the uniaxial tensile tests to evaluate the mechanical to evaluate the effect of low temperature gaseous carburizing on the mechanical properties of 360L stainless steel. The result shows the LTG state slightly increases the tensile stress of 360L stainless steel, but reduces its ductility. The fracture surface of the untreated sample is dominated by numerous dimples, which is typical of decal fracture. For the carburized sample, primitive cleavage fracture is observed within the stressed case, indicating a brighter surface case over a ductile core. Next, I will describe the result of fighting fatigue test, starting with the fighting fatigue life. The fighting fatigue limit of 360L stainless steel is 14% lower than that its planned fatigue limit. LTGC leads to an 10% improvement in the fighting fatigue limit, and head stress level is it should be noted that carburized sample exhibit shorter fighting fatigue life than untreated samples. The number of circle to failure graph on the right shows that with the decreasing stress, the fighting fatigue life of carburized sample gradually recovers and eventually exceeds that of the untreated samples. Using SEM, we examine the fighting fatigue fracture morphology. The result shows that all fighting fatigue fractures originated from the fighting fatigue surface of the sample. Fatigue fracture in the untreated sample initiates from the surface. In the contrast, for carburized sample, as the stress decreases, quick initiation sites tend to shift from the surface to subsurface. Next, we examine the style of the fracture, that is, the fighting wheel surface by SEM and EDS. For the untreated samples, the surface shows several damage. We can observe the microcracks, ploughings, plastic deformation, and reverse. In addition, EDS analysis indicates the presence of oxidative wear. So, the wear mechanism is governed by a combined action of abrasive, fatigue, and oxidative wear. The wear surface of carburized sample is very smooth because of the LTGC forms a much harder surface of 360L stainless steel. Is only a few microcracks observed, and oxidative wear is the predominant wear mechanism. The morphology of contact pad is shown here. It should be noted that all contact pads were kept in the untreated condition and were not subjected to LTGC. The contact pad of untreated sample also suffer several wear, particularly in the edge mixed fighting region, where a combined action of abrasive, fatigue, and oxidative wear in the pad is observed. Owing to the higher hardness of carburized case, more pronounced ploughing occurs on the pad, where the dominant wear mechanism remains similar to those in the untreated condition. To further understand why carburized sample show lower fighting fatigue life at high stress, we examined the surface feature of carburized sample after a different strain level and measured their radial stresses. The result shows that at high stress, initial cracks forms directly in the surface of carburized case, which means that damage is already introduced during the first circle of fighting fatigue. On the other hand, residual stress measurements also indicated that although the comprehensive residual stress is not completely relaxed after the first circle, the residual stress in fractured sample turns into tensile stress, which is harmful to the fighting fatigue. So, At the high stress level, the reduction of in fighting fatigue after LTGC is mainly attributed to breaking of the carburized case and the relaxation of the surface residual stress. Next is the conclusion slide. LTGC successfully formed a 30 micrometers carburized case on the 360L stainless steel surface, significantly increasing surface hardness and introducing beneficial comprehensive residual stress. LTGC increases the fighting fatigue limit of 360L stainless steel by about 10%. And at high stress level, the reduction in fighting fatigue level life after LTGC is mainly attributed to cracking of the carburized case and relaxation of the surface comprehensive residual stress. That's all. Thank you.